Aha. Okay. Day off tomorrow. Pretty exciting. Feels like we're getting a lot of days off. Yeah. It's not. Pardon? A day off tomorrow. I was hoping we would finish conditional probability today. We're not going to get anywhere close to it. That's okay. Take our time. Yeah, I was talking to Steve this morning. I was like, well, here's all the things that I'm hoping to get done today. And he's like, well, good luck. We'll see. So we didn't get that far, nearly that far, but we are going to finish section 3.1. And what I want you to do for over the weekend is make sure that you read 3.2 because it's quite a big section. So of course you were going to do that anyways. I know. Read at least 3.2. It wouldn't hurt if you finished all of chapter 3, but at least 3.2 over the weekend. Or I guess you could do it on Monday too. That's up to you. Enjoy. Period. Enjoy. We'll go through it, but it would really help if it wasn't the first time that you were seeing it. So in terms of review, from last day, we started talking about probability and some basic probability rules that we're going to use. What we also said was, okay, well, a lot of these things we know, right? Our brains know already, but we're attaching probability notation and mathematical notation to it. So that might be new, right? And so we started probability. And what were some of the rules we established last day? Probabilities must be between 0 and 1. That's our number one rule, okay? So probabilities must be between 0 and 1. When we first introduced that rule, though, we didn't have probability notation, which we do now, right? Because we introduced it later. So how about we translate that into generic probability notation? So if a probability of A, a generic A, has to be between 0 and 1, how can we show that? Well, we can say it must be between 0 and 1. Inclusive, right? Because a probability is allowed to be 0. If it's never going to happen, the probability is 0. If it's always going to happen, it would be 1, right? And so they're allowed to be 0 or 1, so we have to include them. Okay. We also said that the total probabilities of all the possible outcomes, so if we've considered all possible outcomes, then the total probability must sum to 1, right? So the total probability of all possible outcomes must be 1. How can I write that in probability notation? Well, we have the probability of S, and remember capital S is the sample space, which is the list of all possible outcomes, right? Or the set of all possible outcomes. So the probability of S must be 1, right? So we had to introduce these concepts, right? But now we can summarize these concepts using just this probability notation, right? And I'll make a note here. Where S is the sample space. And the sample space, remember, is the set of all possible outcomes. Then we said, okay, well, one of the things that I could calculate is the probability of A or B. But then we said, okay, well, there could be overlap, bless you. So then we would need to subtract that overlap. We did start with a special case where they were disjoint, but you'll see I'm going to write out the general formula. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Yeah. So we worked our way up to this formula, right? And so given any three of these components, we'll be able to solve for the fourth one, right? And so, and one thing where we started was that, okay, if A and B are disjoint, then we don't have to subtract that overlap because why? Because this probability must be 0, right? If they're disjoint, they can never happen together. So then we're subtracting 0. So it's just a special case where we say if A and B are disjoint, the probability of A and B is 0, right? Since there's no overlap. And if you can believe it, which I think you can because you were there, this is all we talked about last day, just summarized in probability notation, right? But we couldn't start here, that would be insane. So we had to build up to it, right? But that's pretty much all we talked about last day. So I'll say that's the end of the review. Okay. And so far, all our probabilities, we've said, okay, well, if I have 4 possible outcomes, then I can split the probabilities evenly across those, and then I'm able to find the probability, right? 1 in 4, 1 in 4, 1 in 4, 1 in 4. That's not necessarily always the case, right? And so when we have these uneven distributions, we say that we have a probability distribution, which is something that I would give you, right, if you needed it. Okay. But first we need to talk about some different components of the probability distributions. So I'm gonna change my wording a little bit here. So probabilities are not necessarily evenly distributed across events or outcomes, okay? Are not necessarily evenly distributed across events or outcomes. In those cases, we would use a probability distribution, right? We can use it if it's evenly distributed as well, but then they're kind of unnecessary. I'll show you why. In those cases, we use a probability distribution. And I guess I should say to establish the probabilities. To establish the probabilities. This is where I'm going to go to the textbook and just steal from them. So for example, if I have 2 dice and I roll them, and what I'm interested in is the sum of those dice, right? Then I can find those probabilities, the sum being 2, right? There's only 1 in 36 ways that that can happen, right? Because it can only be 2 if it's a 1 and a 1, right? Whereas the sum being 3 can happen in 2 ways, right? 2 in 36 ways, because I could have a 1 and a 2, or I could have a 2 and a 1. And those are different, right? But they both add to 3. So then we can find this probability distribution. So in general, we're going to have the outcomes listed up top, and then the probabilities listed down below. So I'm going to steal this here. So a probability distribution is a list of the possible outcomes, right, which is the sample space, okay, with corresponding probabilities that satisfies 3 rules. So rule number 1 is that the outcomes that you've listed, they have to be disjoint, right? There can't be any overlap, because then how are you going to talk about the probabilities, right? And then the second rule we already know, because that's just a general rule for probability, right? Each probability must be between 0 and 1. And then finally, the total probabilities must total 1, which is, again, just a basic rule for probability in general, right? So these are probability rules. Probability rules. Okay. So the only one that we're adding is that we're going to make sure that things are disjoint. Hilariously, in the textbook, they managed to make them not disjoint. So I'm going to fix that. And I have half a mind to email them about it. Why? You'll see. So here, we're given 3 possible probability distributions, and only one of them is valid, and it's our job to figure out which one that is, right? And this is something, right, being able to identify valid probability distributions is something I'll get you to do. So let's go through one together. Wait, oh, I see. Need a little bit of space here. So the first thing we're going to check, right, only one of these 3, right, A, B, C is a valid probability distribution. So the first thing we're going to check is make sure that each of these columns are disjoint. But when I look at this, right, 0 to 25, 25 to 50, right? So I'm just going to clarify that, because that would be overlap, right? Making them not disjoint, right? So here, presumably, but they should be more clear, right? Because then 25 to 50, 50 to 100, 100 and 100 and above, right? And so here, presumably what they mean is this lower one, which is the upper income range, is probably 24,999, right? And then this one can be 25. So you would just step down 1, but kind of sloppy, I think. 24,999. Same thing with this one. This one is presumably 49,999, because it's how many 100,000 or how many thousands they make in a year household income. And then this one, presumably 99,999. Okay, so slight tweak, but this would make them disjoint, which is the first thing that we needed to check for a valid probability distribution. Otherwise, none of these are valid, right? Right, so I'm assuming that this is what they meant, but they tried to be all cool and use K instead of the full 1,000. Right. Okay, so that was number one that we had to check, was making sure everything was disjoint. They weren't, but we fixed it. So now I'm happy with that. Let's keep going as if they were. All right. So if we go back to our list here, all the probabilities have to be between 0 and 1. If I find one that's not, then that discounts that whole probability distribution. It can't be, right? And so here, immediately, I see, you probably saw it too, right? This negative probabilities, right? So for part B, the probability can't be negative. Right, it has to be between 0 and 1. So B is eliminated. Okay. So now I'm choosing between A and C. All right. Moving on to my next one, because everything else looks good. Everything else is between 0 and 1, so I'm not concerned about that. So then the probabilities must total 1. So what I'm going to do out here in the margin is I'm going to find the sum, and I'm going to save us a little bit of computing time and say that the sum here, if I add up 0.18, 0.39, 0.33, and 0.16, they add to 1.06. Oh my gosh, that means it's out, right? Because they have to add to 1. But surprise, surprise, C is going to add to 1. If you go through 0.28 plus 0.27 plus 0.29 plus 0.16 does equal 1. Yeah. But I want to write out the reasons here, right? The total probability must be 1. C, this is a valid probability distribution. This is the valid probability distribution. Lazy probdist. So now, right, if we know that C is the valid probability distribution, right, now we can say, all right, what's the probability of a household income between 25 and 49,999,000 per year, right? Well, that's 0.27, right? So now we can use this probability distribution, even though they're not evenly distributed anymore, right? Much like in real life, then we can find these probabilities still. Okay. Okay. So we can use the probability distribution now in C to find the probabilities for example, the probability, and I'm going to use this same notation here, the probability of making more than 100,000 per year, okay, for household income, I'm just going to write it as the probability of 100K or more, right, with the plus, just matching that same notation here. I drew over the K, I guess, but it's there. Is 0.16. Oops. So the probability of making $100,000 or more per year is 0.16. Okay. If I asked you what the probability was of making less than $100,000 a year, what would your brain do? 1 minus, right? Because the total probability, I'm looking at everything else. And so what we're doing, we would never call it this, but what we're finding is the complement of an event. Okay, the complement is just the opposite of that thing happening. Okay. So, yeah, I'll just steal the complement definition here. Just jump right in. Because I do find that intuitively we already understand the complement, but we just would never call it this, probably. So the complement of an event, if any generic event A, is denoted by a superscript C, or sometimes I get lazy and I use just a little prime. But if you've taken calculus, that gets confusing because that could be the derivative. You would understand from the situation though that it's not, but anyways, try to use C, but sometimes I slip up. And the complement of A is basically everything that's not in A, right? So even though we had other categories here, right? So here 100,000 or more, there were 3 other categories, but all of those are not 100,000 or more, right? And so then we can lump those all together as either they make 100,000 or not. So usually when I'm reading the complement of A, sometimes I'll just read it as not A, right? So, here. The complement of A, so A to the power of C, is the complement of A but I read it, I'll put in brackets, I read it as not A. Right. Usually because I find that that kind of puts me on the right track in terms of solving problems, right? The complement of A doesn't really tell me anything, but if I think of it as not A, right, then I've got a pretty good handle on it. Yeah. And so there's a couple of different versions, but they're all derived from this one formula. So if there's either A or not A, then those are all the possible outcomes. So of course, those probabilities have to add to 1, right? Because A and not A must be the sample space, right? So they have to add to 1. So then we can rearrange this. The probability of A is 1 minus the probability of not A, right? That kind of thing. And of course, vice versa. Usually my go-to is the probability of not A is 1 minus the probability of A. So then if A, let A be a household income of $100,000 or more, a household income of 100K plus, right? Then we already established that the probability of A from that probability distribution was 0.16. Right? So then we can find the probability of not A. Your brain already does it, right? So it's nothing crazy here. The probability of not A is 1 minus probability of A, 1 minus 0.16, which puts me at 0.84. How do I interpret this probability? Not A, right? It means a household income less than 100,000, which would encompass everything below 100,000. So therefore, the probability of a household income less than 100,000 per year is 0.84. One thing to remember when you're answering these questions, probabilities are between 0 and 1, right? So even though you probably want to report this as 84%, right? Unless it's asking for a percentage, you're going to leave it as the decimal, right? So we usually want to convert it to a percentage, right? But you're only going to do that if it asks for a percentage. Okay. So just a quick note. If a question asks for the probability, you're going to give the decimal version, right? It's between 0 and 1. And then if it asks you for the percentage, which it could, right, then you have to convert it to a percentage. So if a question asks for the probability, you must give a value between 0 and 1. Whereas if it asks for a percentage, of course, you're going to convert it to a percentage. Whereas if it asks for a percentage, you should convert to a percentage. Pretty basic stuff, but doesn't hurt to say it. And I say it because I get so many questions. It's not taking it. Doesn't like it. Well, wants a percentage or it wants a probability. In general, any math that we do, we're going to use the probabilities, right? So we're going to use the proportions because the percentages just don't behave the same way necessarily. And so let's see here. Any math that we do, I feel like I want to put math in quotes. Any calculations, right? Any math that we do involving probabilities should be done using proportions. Should we close the back door? Would someone mind? They're so noisy out there. Thank you. Should be done using proportions. Right, between 0 and 1. And you can try it, right? Think about 5%, that's 0.05. If you're doing 0.05 times 0.05, you don't get the same value as 5 times 5, right? Decimals don't work that way. So that's why it's really important. Okay. Good. Speaking of math, oh boy, here we go. So just like we started and we talked about disjoint events first, and we kind of established the addition rule for disjoint events. We're going to start doing the same thing, but for independent events. So independent events is slightly different, and I'm going to steal from the textbook here because couldn't have said it better myself. Oops. And I usually have something very similar, so I may as well just use this one. So independence, or come on. Independent events are another one of those special cases, right? Where we're going to start there and we're going to start building a formula, and then we're going to get to the general formula, but we don't get there today. We'll save it for next week, something to look forward to, right? But independent events. Okay. A random process, remember, is something that generates a random outcome. So rolling a die is a random process. Flipping a coin is a random process. Drawing a card is a random process. Okay, so okay. You can read starting from here. I'll read it, but it's way in the corner. He'll go away. So two processes are independent if, man, it's just not my day. Okay. At least I look good, right? They're independent if knowing the outcome of one provides no useful information about the outcome of the other. Oh. Oh. Come on. There's a bug nest. Just not my day. That's okay. But by now you've had time to read the whole thing. So some independent events or outcomes, right? If I roll a die and I know that it turned up a 2, I know that that has no effect on what my other die roll is going to be, right? Those probabilities are independent of each other, right? Whereas if we're talking about things like stock prices, for example, right, they kind of go up and go down and crash together and flourish together, right? And so knowing that another stock went up, right, then I have a pretty good idea that whatever stock I'm interested in probably also went up, right? And so it all hinges on the probabilities, right? Does knowing the outcome of one affect the probability of another? So we're going to start with the scenario where it doesn't, right? So, right, if I flip a coin and I tell you, okay, oh, if I flip tails, that tells me nothing about the probability of rolling a 2, right? The probability of rolling a 2 holds steady. It's still 1 in 6, right? And so those are what we call independent events. Okay? And they're quite common. They happen often. So opens up a world of questions that we can talk about, right? If I'm drawing from a deck of cards, right? Knowing that I drew a king, for example, right? If I don't put it back, then the probability of drawing another king is slightly lower than it was before, right? Making them dependent events. However, if I replace the card, right, then that probability doesn't change, right? So from a deck of cards, we can have independent situations or dependent situations. Dependent on them mowing the lawn. Okay, so we're going to start by considering the special case where we have independent events, and we're going to talk about, okay, well, what's the probability of a series of independent events happening? Okay. So we will start by considering the special case of independent events Then move on to, and just like disjoint, I call them not disjoint. So now I call them not independent events. You can call them dependent. I just, for some reason, I don't. It's weird. Then move on to not independent events. I guess the quote doesn't need to be around the events, not independent. Right? You can call them dependent if you want to. But I just call them not independent. I think my brain, what happens is I like to have just one thing that I keep track of, and then everything else is not that, right? Otherwise, there's so much terminology. Okay, so what does that mean for us? Usually what I find is when I introduce independence, so we started with disjoint outcomes, right? That was a special case. And then now we have independence. And usually it's very confusing, and it was for me too in the beginning, right? Keeping track of which one is which now that we have kind of two special cases. So I just want to outline the differences between the two. So disjoint has to do with the outcomes, right? No outcomes in common, okay? And if they're disjoint, the probability of them happening together is 0. That's just a fact because they can never happen at the same time. Making me work for it today. All right. Whereas independence, come on, just independence has to do with the probabilities, right? Does knowing that does knowing that A happened, does it impact the probability of B happening, right? Independence says, well, no, they're independent if it doesn't, right? And so let's see here. Let's outline disjoint versus independent. Only because I know that's a kind of a sticky part. Disjoint is two events with no outcomes in common. Two events with no outcomes in common. Which also means the probability of A and B is 0, right? If there are no outcomes in common, the probability of them happening at the same time must be 0. Okay? Whereas independent is referring to the probabilities. Is referring to the probabilities. Okay, so it's the difference between the outcomes and the probabilities of those outcomes. Okay, so does knowing the outcome of A affect the probability of B? Does knowing the outcome of A affect the probability of B? If it doesn't, or if not, right, then we can say that A and B are independent. So if not, A and B are independent. So, okay. I'm just gonna jump right in and steal the multiplication rule for independent events. And then we'll backtrack and we'll talk about them, okay? The textbook, of course, does a better job of building up to it, but you're welcome to read that, of course. But sometimes I find kind of knowing where we're headed is a little bit more useful. Okay. Just highlighting that it's only true for independent processes. Okay, so a little bit wordy, but let's break it down. So if A and B represent outcomes or events for two different and independent processes, right? So if they're independent, then the probability that both A and B occur can be calculated as the product of the separate probabilities. So the probability of A and B, if they're independent, we can just find it by the probability of A times the probability of B. So it's really, really important that if A and B, and I would just say are independent, okay, then we can find the probability of A and B as the probability of A times the probability of B. It hinges on them being independent. It's no longer true if they're not independent, right? So it's going to be very tempting to use this formula for things that are not independent, right? But I'll show you the alternative that you have. We can even think of, as long as we have K independent events, then we can still multiply them through, right, to find the probability of all of these happening together, right? This A1 and A2 and A3 and A4 and all the way up to AK. Put a stretch or a question? Stretch. Phew. So let's summarize this big box here. So if A and B are independent, then the probability of A and B is the probability of A times the probability of B. Right, that's what that box is saying. And then we can extend it to more than two events. That's fine. Right. Remember I said, if you see the word, or if you think the word or, you're going to be adding, right? And if you see the word and, you're going to be multiplying, right? So now we're seeing that, okay, so A and B have to happen, right? So now I have to multiply these. I want to make a note here. This is only true if A and B are independent. Okay. Another way, and how I usually end up using this formula, is not necessarily to find the probability of A and B and C and D, for example, right? That's usually how we end up doing it. Usually I use this to check if two things are independent, right? That means I need to know the probability of A and B. I need to know the probability of A, and I need to know the probability of B. But if I know those three probabilities, then I can check mathematically whether they're independent or not, right? I'd multiply the probability of A times the probability of B. And if it is the same as the probability of A and B, then I can conclude that they're independent. They have to be exactly equal. Okay, so that's kind of a glitch, but we'll do an example of how that works. But for now, let's write a little note here. If we know the probability of A and B, the probability of A and the probability of B, we can use this formula to determine if A and B are independent. We can use this formula to determine whether A and B are independent. We'll build to that. So let's do an example. I'm stealing just a quick blurb from we'll accept this as fact. About 9% of people are left-handed. There, I don't know. What does that mean? It means the probability of randomly selecting a left-handed person must be 0.09, right? And so here, what we would say is, therefore, the probability of randomly selecting a left-handed person is 0.09. And looks like a 7 maybe. Although I always draw lines through my 7s, so there's no confusion. Okay, so if we let L represent picking a left-handed person, right? So if we establish our notation here, let L be selecting a left-handed person. I know there are ambidextrous people, those lucky people, but I think even they would say that they have a dominant hand, right? My left arm, I think you could chop it off and I wouldn't notice for days. It's just like, doesn't do anything, and it can't do anything. So I'm a strong right-handed person, okay? And so let's just assume that there are only those two things, right? Otherwise it gets too complicated. And so really what we could say is we're gonna let R, seems reasonable, represent selecting a right-handed person. R is really the complement of L, right? So is really the complement or not left-handed. If you're not left-handed, you're right-handed. Right? So what we know then is that from here, we said in a very long-winded way, the probability of randomly selecting a left-handed person is 0.09. I could wrap this up really nicely with some shorthand, right? By saying what? By saying the probability of L, which is randomly selecting a left-handed person, is 0.09. Right? That's the same as what I said up here. You can see the perks of probability notation, even though it takes some getting used to. I know that, right? So then the right-handed person is really not L. So then the probability of selecting a right-handed person is the same as the probability of not L, which technically, right, is 1 minus the probability of L. You already got there a long time ago, I know that. right? 1 minus 0.09, bless you, it's 0.91. Which means the probability of randomly selecting a right-handed person is 0.91. Right? Okay. So now we can use these probabilities to find probabilities of a series of people who are either left or right-handed. So I'm going to steal some questions here. I'm going to sneak another one in there, but so if we're selecting 5 people at random, right, then let's just say even here on campus, if I randomly select 5 people, then it's pretty safe to assume that they're going to be independent of each other, right? Especially for left and right-handedness. There's nothing that says, well, because I'm right-handed, you must be left-handed, and you must be right-handed, and you must be right-handed, right? We're all independent of each other. It would be if I was sampled and both my parents were also sampled, but that wouldn't be random, right? That would be terrible sampling, right? Because we're not necessarily independent of each other, right? For example, if both my parents are left-handed, I'm probably more likely to be left-handed than right-handed, right? That kind of thing. And so if we're selecting from a large enough group randomly, we can assume that the left and right-handedness of people is independent. Okay. So here, I'm going to say, since we are randomly selecting people, right, ooh. So since we're randomly selecting people, I'm going to assume it's from a large population, right? Then there's no reason to think that those things would be dependent of each other. So here I'll say, presumably from a large population, it is safe to assume the left or right-handedness of these people is independent of each other. The left or right-handedness, I don't know how to say that. Handedness of these people is independent of each other. Because that was a big thing, right? One of the things that we are assuming for now is that we have independent events, right? And so now we're going to consider a series of independent events. Okay. So first question here. If I am picking 5 people at random, right? What's the probability that all are right-handed? So then let's move that down here. You can use just the formula that I gave you here, right? A1 is the first person, A2 is the third person, or no, that doesn't make sense. A2 is the second person, A2 is the third person, A4, A5. right? And then we could multiply those probabilities. But my brain doesn't work that way. And so how I work these questions is I think, okay, I go out and I have to pick person number one, right? And so I make a slot for person number one. So here I have person number 1, 2, 3, 4, and 5. Okay, so they're just waiting for whatever probability I give it, whatever I need to have happen. Okay. And so now I'll write the probability up above here. The scenario that I'm after here is whether all are right-handed. So that means person number 1 has to be right-handed, and person number 2, and person number 3, and person number 4, and person number 5, right? And so all of these are right-handed with a probability of 0.91. Okay. So I can jot that down, 0.91, 0.91, 0.91, 0.91. And like I said, in my head, I say, okay, 1 and 2 and 3. So I'm going to write that down here. And means I multiply. So here we have this series of independent events, and that's when I can go ahead and multiply through. So the probability that all are, or maybe I should say all 5 are right-handed. Right? Multiplying across, well, you'll see that it's 0.91 to the power of 5, right? And sometimes I get people who are all concerned, well, I don't think I'll remember to raise it to the power of 5. That's okay. There's really no difference in going through and just multiplying through here, right? I'm just cheating a little bit. Okay. Because I see that it's 0.91 to the power of 5. But there's no harm if you wanted to just go through and multiply through, right? We'll get to the same answer, which is approximately 0.26240321451. Just in my head, you know, no, not even close. Okay. So I like to use these slots. If you don't need them, that's great. Right, but I find that they're kind of useful because now I want to add a part that's not in this list here. So I'll call it A part 2. What's the probability that the first person that I pick is left-handed and the remaining are right-handed? Okay. I'll jot that down. What is the probability that the first person selected is left-handed and the remaining people are right-handed? And the remaining people are right-handed. So again, I've got this series of independent events. So I'm going to go ahead and I just make little 1, 2, 3, 4, 5. And now that we've seen kind of this is it properly, that's not usually how far I go. I just make slots and then I put the probabilities on here. right? So now I'm going to force this first person to be left-handed, and that's going to happen with a probability of 0.09, right? And then I have the remaining are right-handed, so 0.91, 0.91, 0.91, 0.91. And in my head, right, I'm saying, okay, person number 1 has to be left-handed, and person number 2 has to be right-handed, and person number 3 has to be right-handed, and person number 4 has to be right-handed, and person number 5 has to be right-handed. So I'm going to multiply these guys through. If ever you're setting up this kind of series of consecutive events, then you're going to be multiplying. But what happens if I multiply this out? I get, make sure I pick the right number here, 0.0617174649. Oh. Or.
No, never mind.
Okay. Okay. So this isn't the same as what's the probability of at least, or sorry, what's the probability of 1 left-handed person and 4 right-handed people, right? This is one of those scenarios, right? The other scenario would be, okay, well, maybe the left-handed person was the second person. So that's another one of those scenarios I could draw out. I could find that probability. What if it was a third person? Okay, fine, I'll find that probability. What if it was a fourth person, right? Fine, I can find that probability. Fifth person, same thing, right? We're not quite there because we're not going to do it, but like that, that seems really tedious and boring, right? We're going to use the binomial distribution for that, right? But that's how we would answer that type of question. If it's just one left-handed person, right, then we would have to take into account that, okay, there are 5 different scenarios that could happen, right, where there's one left-handed person. But for now, we'll stick to these guys. So same thing. If we want to find the probability that all are left-handed, so again, right, 1, 2, 3, 4, 5. You don't have to use the slots. I just find that they're useful, right? So now if they're left-handed, same thing, 0.09, 0.09, 0.09, which is 0.09 to the power of 5, which is roughly I got scientific notation, so you might not have the 1, 2, 3, 4, 5 zeros. 59049, roughly. Very, very small probability, right? So now the probability of rolling 5 ones in a row, well, 1 in 6 times 1 in 6 times 1 in 6 times 1 in 6 times 1 in 6. Is that probability any different from all the other combinations? No, right? If you're rolling a die 5 times, it's always the probability is 1 in 6, regardless of what the number is, right? But you'll play around with that on the assignment. Oh. See. What's the probability that not all of the people are right-handed? Okay. So that's not the same, right, as everyone being left-handed, right? If not all the people are right-handed, that could mean 4 people are right-handed, 3 people are right-handed, 2 people are right-handed, 1 person is right-handed, 0 are right-handed, right? That's this outcome here. And so now we've got this tons and tons of different combinations that we can consider, or we can kind of cheat a little. It's not cheating. We can be clever and we can use the complement, right? And so not all people are right-handed is basically saying what's the probability of all are right-handed makes me think of like when you're a kid and you're playing on a keyboard and it's all like drums and like, yeah, sounds so good. Right, so what we're doing is, well, okay, not all people are right-handed. That's really just taking the complement of all of them being right-handed, which, surprise, surprise, we already found. That's usually the case, right? These probabilities that I ask you for build on previous probabilities. So if you find that you're constantly recalculating probabilities, probably not doing it right? They usually build on each other. And so here we already know what's the probability that all are right-handed. Well, we know that it's roughly this, which I'll steal. Copy. Which is 1 minus the probability that all are right-handed. And this is from part A, of course, 1 minus paste. Oh, sneaky. But then I didn't use all the decimal places earlier. So here we go. It's roughly 0.37597. A little bit more because I showed a little bit more, but that's probably close enough. Okay, so you could figure out all the different scenarios where not everyone is right-handed, but that seems like a lot of work, right? And so I rarely make you do that much work. You're just clever about it. All right. So like I said, the last thing I want to show you is how do I use this formula to see if 2 events are independent or not, right? What we said was, okay, well then I need to have those 3 probabilities, otherwise I can't check for it. So here's an example. If we shuffle up, combine the 2, a deck of cards and draw 1 is the event that the card is a heart, independent of the event that the card is an ace. Okay, so now we have to think back to our deck of cards. You'll notice on the assignment that I posted from last day, there's the first probability or the first card question has the deck of cards that you can use if you want, right? You can refer back to it if you're not that comfortable with cards, but we should probably know the basics by now. So the things I'm interested in are drawing a heart or an ace. So let's establish shorthand for those and say, okay, let H be drawing a heart. And let's let A be drawing an ace. I want to know if those two things are independent of each other. Okay. So first thing, we know all these probabilities, right? We know that the probability of drawing a heart, there are 13 out of 52 cards that are hearts. And so the probability is 13 in 52. The probability of drawing an ace, there are 4 aces in a deck, and so that's 4 in 52. And finally, the probability of a heart and an ace, there's only one of those cards, right? And so 1 in 52. Right? So we know these 3 probabilities from the formula. The 3 probabilities from the formula. Right? And that formula says that if A and B generically are independent, then the probability of A and B will be equal to the probability of A times the probability of B. I'm going to work our minds a little bit and just say, okay, well, these are generic outcomes, just placeholders for A and B, right? But I have H and A. I think it would be too easy to replace the A's with A's. So I'm going to replace the A's with H's and the B's with A's. You don't have to do that, but it's good to get in the practice of just kind of, okay, these are just placeholders. So whatever I want to put in their place, I can. A goes where A is and B goes where B is. It doesn't matter what they are. Just keep them separate. Of course, A and B is the same as B and A, and the probability of A times the probability of B is the same as the probability of B times the probability of A. So in this scenario, it doesn't matter, right? But in the next general formula, it will matter a lot. And so it's good to get in the habit of, okay, these are just placeholders and I can replace them with whatever I want. Okay. So if I want to find, or if I want to see if the probability of H and A is equal to, and so I usually put a little question mark until I've established whether they are or not. I wouldn't dream of saying they're equal if I don't know. Well, that's going to be, is it equal to the probability of H times the probability of A? Right? Probability of the first one times the probability of the second one. Doesn't really matter. So now I can take these probabilities and I can plug them in and I can see if they're equal.
I have a question about the question.
Uh-huh.
It says if we shuffle up a deck of cards and draw one,
Yeah.
the event that the cards are independent of the event that the cards makes. When if you draw one, mean that you now have 51 cards?
But as you're about to draw it, that's when we're talking about the probabilities.
Okay.
So because you've got a full deck and you're about to draw a card, the probability before you look at that card, right, the probability is going to be out of 52. If that helps. Can be tricky. So then I know that the probability of it being a heart and an ace is 1 in 52. And I want to know if that's the same as 13 over 52 times 4 over 52. Now my calculator just gives me the reduced fraction as an answer, And yours probably does too, if you change some settings somewhere, so it might be worth looking into. Because I know some of the answers on the assignment ask for the reduced fraction. But if you can't figure out how to get your calculator to do that, you can just Google your way to some reduction calculator, I guess. I don't know. Reduced form. It's for the birds. If I do this multiplication, it does indeed end up being the same, right? You want to make sure that you use the exact values because you don't want to be rounding, because then they wouldn't be the same anymore, right? And so what we're going to say here is that since, maybe I'll highlight here, since the probability of H and A is the same as the probability of H times the probability of A, we can conclude that H and A are independent events. It's really important. Okay. It's really important that they're exactly equal, right? Otherwise, they're not truly equal. Okay. So they must be, question? They must be exactly equal. Good to the last drop. And we'll stop there. Any questions? You guys packed up 5 minutes ago. Go have a good weekend. Thank you. Bye, Natalia.